1996 E&M number 1. Let's see here. They've given us a solid metal sphere of radius A charged up to an electric potential. And then we're going to isolate it by putting a shell around it of inner radius B and outer radius 2B. And you need to keep in mind we've measured the voltage, but we haven't directly measured the charge. Kind of like we did in class with voltmeters, we measure the voltages, but we didn't measure any charges directly. So for part A, they want us to determine the charge on the solid sphere before it's surrounded by the outer shell in terms of the given quantities. Now for a spherical charge or a point charge, we've previously figured out that the electric potential is kq over r. In this case, we know what r is, k is a constant of the universe, and v naught is one of the givens. So we can just rearrange this equation to solve for the charge on the sphere. And in this case, the radius is a. Now, we could also say k is 1 over 4 pi epsilon naught. So if you prefer that, you can have, instead of k, over 4 pi epsilon naught in its place. All right, B. That guy has 4 parts. Magnitude of the electric field is a function of r for the regions indicated below. All right, now, the electric field from a point charge is going to be kq over r squared. And in this case, q is going to be this stuff. Oh, whoops, you know what? I can't do basic algebra. Let me fix this. We're going to multiply by r and divide by a. So divide by k. So that's v naught r over k. And in this case, r is the radius a. Okay. Or you could also say 4 pi epsilon naught v naught a. All right. Apologies. Silly algebra mistake. Okay. So for the electric field, where Q is in terms of the given voltage, well, in this case, V naught A over K, we're going to have V naught A over R squared, where this K and that K are going to cancel out. Here's our basic expression. Now for part 1, R is less than A. Well, inside our ball of charge here, if we put our dotted line there of radius less than a, we're going to find that the electric field is 0 because the electric field inside any conductor is 0 because all of the charge always goes to the outside of the conductor. All right, part 2, in between the two of them, we will have, here, let me change colors. We will have green here. Now in between them, we have a radius bigger than A. We have now enclosed all of that charge, less than B. So for A less than R less than B, we are going to have E is V naught A over R squared. These are in terms of the givens. Keep in mind that Q naught is not one of the givens, so we shouldn't have that in our answer. And as long as, let's see here, for potential greater than 0. So if the potential is greater than 0, that means the charge is greater than 0. It's a positive charge. That means we're going to have an electric field pointing radially outward. All right, 3. Now let's change colors again. We'll do blue. Inside that charge, inside that conductor, inside all conductors, the electric field is going to be 0. This is always going to be the case for electrostatics. The electric field is 0. that should give you an indication that if this guy here, let me get rid of these things. If our inner sphere is a positive charge, in order to have zero electric field inside this shell, we're going to have the inner surface with a negative charge. That way, once we have gone into the into the conductor, and we draw our Gaussian surface here, we've enclosed a net zero charge. The result will be that the same charge, the same size charge that resides on the inner sphere is going to reside on the surface. And then when we get to outside here for part 4, way out here, for radius greater than 2b, we will have enclosed just that positive charge. We will have a plus and a minus, they cancel each other out, and then a plus. And so what we see here is just the plus charge. So for part 4, r is greater than 2b. The electric field, again, is going to be kq over r. In this case, v naught a over r squared again. And again, it will return to radially outward. Naturally, if the electric field is 0, there is no direction. Oh wait, I just did C. I entirely skipped part B. My apologies. That is part C. All right, let's back up and do part B. The induced charge at the following, the inner surface, the outer surface. Okay, so I've discussed that a little bit. We will need to have the same amount of charge on the inner surface as we have in the central sphere. So the inner surface of the shell, so Q inner, is going to be equal to negative Q naught, which is also this guy with a minus sign. So minus V naught A over, in this case, the radius will be, for the electric field, the radius would be B, but we don't care about that right now. All we care about is the size of the charge, which is going to be V naught A over K with a minus sign. And Q outer will be the same as Q naught, also a positive. And they don't care about the size at all. They don't care about sigma. All they care about is the charge. All right, so that'll be plus Q and that'll be minus Q. All right, now part D. Does the inner sphere exert a force on the uncharged hemispheres while the shell is being assembled? Well, yes. If you notice this bar here and that bar here, that's to indicate that we have a hemisphere here and we have a hemisphere there. And initially, we have no charge on either hemisphere. But while it's being assembled, what's going to happen is, so we've got pluses and minuses spread evenly throughout everything. And what's going to happen is all those minuses are going to get pulled in, and these minuses are going to get pulled in until the amount of those minuses is equal to the charge here. So those charges getting pulled in is going to be the net charged. And that is going to be closer. So for part D, negative Q pulled toward Q naught to inside of shell. It's closer than the residual positive Q on the outside that I already discussed. So the net force is going to be towards inside. It's going to be pulled towards the inside. All right, part E. Let's see, I'm going to have to pause and get rid of all of this stuff so I have space. All right, so the inner sphere still has the same charge, but it's surrounded by more charge. So we have a plus here, and a minus here, and a plus here. So if you're going to walk, here's you, if you're going to walk from the outside here and get to that surface of that sphere, you're going to have to first climb this mountain, deal with that valley, and then climb back up that mountain again. So what we have is a voltage due to 2B, which is going to be K Q naught over 2B. Then we have a voltage at B, which is going to be minus K Q naught over B. And then we still have our voltage at radius A, which is K Q naught over A. But the voltage in getting from here all the way to there is going to be the sum of these three voltages. So V new is going to be VA plus VB plus V2B. Adding these three expressions together, we're going to have K Q naught, and then we'll have 1 over A minus 1 over B plus 1 over 2B. And now we just have to multiply things. This guy gets multiplied by a 2B, this guy gets multiplied by a 2A, and that guy gets multiplied by an A. And then the whole denominator is 2AB, and is multiplied by KQ naught. So let's see here, 2B minus 2A plus A, these guys are going to turn into minus A. So V new is going to be KQ 2B minus A over 2B. And let's move the A over here. And if you remember, unfortunately, I erased it. KQ over A, that was V naught. So V new is going to be V naught times the fact that now we have a shell of thickness 2B wrapped around it. And that makes our new voltage, again, if you're going to walk from outside very far away to then go stand on the surface of that sphere.